Hello friends, we are about to start the topic where we'll see how to design a controller or control unit using either hardware approach or microprogrammed approach. I know this is one of the most scariest topics for all the students, but trust me, I will try to make it as simple as possible. But before we jump for the actual designing of controller, we'll have to know some of the basic of some hardwares which we'll be using in our control unit designing. In this video, we'll see those types of hardwares, and also we'll see about different types of bus architectures we have in our CPU.
So let's the basic concepts of control unit. So whenever we talk about control unit, we have two basic approaches to design a control unit. We have two different major approaches. One is hardware approach and second one is microprogramming approach to design a control unit. So in our upcoming videos, we'll discuss in detail about both these approaches. In today's lecture, we'll try to see the basic concepts of control unit, like what are the fundamentals of control unit, what is RTN and descriptions, what are the different types of buses we have in control units, and so on. Fine. Now, whenever we talk about CPU, central processing unit, this CPU has two major components. You have to note it down. In CPU, we have two major components. Number one is called processing section and number two is called control unit. Now I will try to make it very simple. In simple word, what is processing section? Processing section is nothing but the set of all hardwares which are responsible to work some operation. Find all the hardwares. Whenever we talk about processing section, this processing section deals with all types of hardwares which are there inside of CPU. Fine. And the second part is control unit. Control unit is like a boss. Control unit will generate the signals. It will generate the control signals to control the processing section. You understood that? Processing section is nothing but a set of hardwares which are there inside CPU, and control unit is responsible to handle all these hardwares by generating some control signals. It will generate the signals. The signal will be going to the particular hardware unit and the hardware unit will act according to the signal. Fine. Now, control unit's responsibility is to drive the associated processing hardware, whatever I said. And also, your control unit is associated or synchronized with the master clock. Fine. In control unit, basically we have three different units, input units. In this, suppose this is your control unit, CU. You will have three different inputs. Number one is nothing but your master clock. Your control unit will be connected with a master clock to track all the timings and all, clock signals and all. Fine. Second one, the second input of your control unit is nothing but the status information. Status information means the information which tell you about the hardware where you are going to operate, whether it's functioning or not, whether it's busy with some other work or not. It's kind of status, it will say. Fine. First is master clock, second one is status information, and the third one is nothing but command signal. So command signal is nothing but when you want to stop your control unit, say, forcefully. So some command you can provide like stop, restart, clear. Those kind of commands you can put by using this command signal input line. So there are three input lines to control unit, and there is only one type of output it will generate. That is nothing but the control signals to control the processing section hardwares. Fine. So yeah, whatever I said, these are the three inputs we have, and output is nothing but the signals. I hope the very basic of control unit is fine for you now. What is processing section you understood? What is control unit you understood? What are the inputs in control unit and what is the output of control unit? I think you understood that. So next, we'll see some of the basic RTN operations or register transfer operations. So in our previous lecture, I told you, whenever you convert your program or whenever your compiler convert your high level program to machine level instructions, there are two different ways. One is register transfer notation and second one is your assembly notation. So most of the time we deal with register transfer operations or register transfer notation whenever we design some control unit. Now register transfer notation or operation is very simple. How to deal with that? Suppose you have a register B and you have a register A you want to write a code that you want to move everything from A to B. So in RTN we write like this. In previous lecture also we have seen the same thing. B, this cursor symbol A means whatever there inside A, it will be coming back to B. Fine. Now if I ask you to draw the block diagram for this particular instruction, how you can write? This is the block diagram, right? You have a register A, you have a register B, so everything from A is coming to B. Fine. Now how to declare the registers in RTN? This is how. These are the variable names A, B, P, C. You can put your own variable name X, Y, Z, whatever you want. So A in square bracket 8 means you have a register name A that can hold 8 bit of informations. You have a register B that can hold 8 bit of informations. You have a register PC that can hold 16 bit of information. Like that, you can have your own variable and own number of bits you can define. Fine. So now some more operations we will see. Suppose in any register, suppose I have a register PC where I have 16 bits 0 to 15, and some of the bits from my register PC I want to copy to some other register. So forget about this name. These names can be X and Y also. These are some variables only, nothing else. Although PC means program counter we are indicating, but you can put any other variable also, A, B, C, D, whatever you want. Suppose I have some variable, some register PC where I have 16 bits 0 to 15, and I want to copy some of the bits from here to some other registers, maybe PCH they have given. You can put X, Y, Z, whatever. So how to do that? So PCHI is a new register that can hold 8 bits, and there what I want to do, I want to copy some of the bits from my PC. What are the bits I want to copy? The 15 to 8 means most significant 8 bits I want to put to PCHI. 15 to 8 means bit number 15 to bit number 8, everything will be copied to PCHI here. This is how we can write. Fine. And then also we have some other operations we can perform like this. Suppose I want to exactly copy the 7th bit of register A to 0th bit of register B, I can simply write like this. B is square bracket 0, this cursor symbol, A is square bracket 7 means whatever there in 7th bit of A, it will be copied to the first bit or 0th bit of B automatically. Fine? I hope this is fine for you. Okay, we'll see some more operations. Now this block diagram and this instruction is clear for you. Whenever I have written B, cursor symbol A means I'm moving everything from A to B. Now if I ask you that put some condition, I don't want to transfer everything from A to B anytime, all the time. I want to have some condition or some switch kind of thing that will decide whether A to B shall I move or shall I stop now. So I shall have some switch kind of thing. So in digital system you have gone through a concept called input enabled or enabled signal, right? So here also you can do the same thing. What we can do, we can put an enable input line like this in B register. So whenever this enable line is 1 means A to B movement will be happening, means I want to move from A to B if it is 1. If it is 0 then I don't want to copy. It's like a switch. In this diagram every time I'm sending A to B, but here I'm not sending every time. Whenever I am just making it to 1, I'm transferring, otherwise not. It's a switch now. Now how to represent this block diagram in RTN? This was very easy, right? Like this we have written. Now how to represent this to RTN? Like this. We will write E then colon B to A. This is acting like a switch now. I hope this is clear for you. Some more notations we'll see. Now if you understood the basic thing, the next question in front of you, you have to design or you have to draw a block diagram. I will give you the RTN. RTN will be there in front of you. Based on the RTN, you have to draw the block diagram. What is the RTN I have given? This is the RTN or the instruction in RTN. I have if A greater than B and D not equals to 0, then A, for whatever they are in B, I will move to A. So how to move from B to A we know, right? How to move from B to A we know. How to move from B to A whenever there are some conditions or some input line we know, right? So by analyzing these two concepts, I think you can easily do it. So what I will do is, please be careful and note it down very well. So this is how it will look like. I will explain each and everything very carefully. So first of all, I know I have to transfer from B to A. So this is the B register, this is the A register. Forget about the whole diagram. Don't see or don't look at the whole diagram as of now. So whatever I am saying, please pay attention. I have a B register, I have a register. I know I have to transfer from B to A. So I am putting this signal. So I am putting this symbol. Fine. I know I cannot put always. I have some conditions. So I have one enable line here. So as of now, I have B register, A register, and I have one enable line. This enable line will decide whether I have to transfer or not. Fine. This side is fine. Now I will come back to this condition statement. Whenever you get this kind of question, first you draw the last mode, then part. Then you come for if part. Then part is B to A. So B to A I have written. I have some if condition, so enable line is there. Fine. Now what are the conditions I have? If A greater than B. That means somewhere I need one comparator that can decide whether my A is greater than B or not. So I have a comparator. This is nothing but a comparator. In digital system, you already have gone through comparator, I guess. So this is comparator that will compare and tell me whether A is greater than B or not. For that, in this comparator, I need the two input signals. So one I am getting from A and one I am getting from B. And this will decide whether A is greater than B or not. So I will get one output. But this is not the only condition I have. I have one more condition also, which is D naught equals to 0. What is D naught? So from this notation, I am understanding that D is nothing but a resistor, and there the position number 0 or bit number 0 is 0. So D is a resistor. This D naught should be 0, and this A greater than B should be true. Then only it will work, right? So what I'll do, this output line, and from D naught one output line, I am putting as input to a AND gate. Means this is also true, this is also true, then it will be working, it will be 1. If this is 1, then only it will be happening, right? Otherwise not. Now the problem is I cannot simply put D naught directly here as input to the AND gate. Why? Because this is 0, right? If you put 0 here, then my AND gate will produce 0. We know this is AND gate. I need both the input as 1. This is 1, I understood. But when this is D naught is 0, I cannot put 0 directly here. So what I will do, I will put one NOT gate here. So that if it is 1, then it will become 0. If it is 1, that means this is not satisfied. So it will become 0. This enable line will become 0. If it is 0, it will become 1. If it is 0, it is 1 means yes, true. And from here, if it is true, then I will get 1. So 1, 1, I will get an 1. This enable line will work now. I hope you understood that. Okay, then we'll see one more RTN, and I will ask you to draw the block diagram. Now see what we have. We have some more conditions. If x is equals to 0 and t equals to 1, then I will transfer from B to A, else I will transfer D to A. I told you, if you get, whenever you are getting this kind of question, please go for then part first, then go for if part. Then part means the result part. What I have to do, B to A and D to A. So I shall have some resistors from where I can transfer B to A and D to A. So please draw the diagram like this. So from B to A and D to A, I'll have some connection. I know that. So D, B, A, I know. Fine. But the problem is I cannot transfer B to A and D to A all together or at the same time. Any one of the signal can be transferred, right? Else is there. Means either this one will be happening or this one. So to choose any one from this, what I can do, I can use one 2-to-1 multiplexer. Fine. So I am using one 2-to-1 multiplexer. Now this multiplexer will decide which one will be forwarding to A. Right? We know for 2-to-1 multiplexer we need one selection line also. This selection line will decide whether if it is 0, then this one will work. If it is 1, this one will work. Fine. Now we'll see how to set this selection line. This selection line will be setting as per this condition. What do we have here? If x is equals to 0 and t equals to 1, that means I have to use one AND gate. Again, I have x is equals to 0. If I put directly 0 here, then I will never get 1 as output. So what I will do, I will use one NOT gate, so that whenever I am sending x is equals to 0, it's becoming 1. And t equals to 1 directly, if it is 1, then 1, 1 will become 1. If so, then what I will do, I will transfer B to A. Fine. That means if it is 1, if the output is 1, I am transferring this B to A. Otherwise, if it is 0 somewhere, maybe this is 1 or for any condition, because if any one of this is producing 0, then it will be 0. We are using AND gate. If it is 0, then I am sending D to A. Understood that? I hope this is clear for you. Now some of the syntax you will see in RTN whenever we deal with control unit. We have some symbols or notation or syntax we have to remember. What are those? These we have already seen. So whenever you want to transfer something from A to D, this is how we write in RTN. Next, whenever you increment the content of A by 1 or B by 1, then you have to write like this: A equals to A plus 1. This is the syntax. Decrement A minus 1. Then OR operation, this is the symbol for OR operation. If you are getting something like this, you have to know that this is OR operation. This is AND operation. Fine, the symbol of AND operation. Then LSR is nothing but logical shift right. So whatever we have seen in Booth's algorithm or in division algorithm, we have performed right shift operation or left shift operation, right? So the LSR is logical shift right of A. So 1 bit will shift it. ASR is arithmetic shift right. Sorry, in Booth's and division algorithm we have seen arithmetic shift, not logical shift. So what is arithmetic shift and logical shift? Maybe I'll make one more video to differentiate these two, arithmetic and logical shift. This is logical shift left, arithmetic shift left. Then rotation shift. This is ROR is nothing but rotation shift right. This one is rotation left. And this is something new for you, right? This dollar symbol. This dollar symbol is nothing but concatenation. So $Q means you are concatenating A and Q. I hope you understood the difference between concatenation and the addition, right? Concatenation means just to place one after another. Fine. Suppose for example I have written like this: ASR in bracket A dollar symbol Q means first I will do the concatenation of A and Q, then I will do arithmetic shift right. This is how we do. Fine. So next we will see some basic concept of buses. So if I talk about bus, I know you already have gone through different types of buses like address buses, control buses, right? So now data buses. So now if I ask you the direction of buses, means if you want to transfer something from one place to another place using bus, what are the different directions we have? We have unidirectional bus. Unidirectional means only one way communication from A to B I can send, not B to A. I have bidirectional when I can send in both the ways. So in this diagram we will discuss about the bidirectional bus architecture. Now don't be confused with this diagram. This diagram is very simple. As of now, forget about the diagram. Just forget about this x2, xn, y2, yn. Also this part you can just eliminate. We'll discuss only about this part. It will be very easy for you. I have a point x1 and I have a point y1. I want to send something from x1 to y1. That's it. So what I will do? I'll put a block like this, right? I'll put a wire like this from x to y like this, simple wire. But in between I have a tri-state buffer. What is tri-state buffer? In digital system you must have been gone through. Tri-state buffer is nothing but again like a switch. When this is 1, if tri-state buffer is 1, then only the transfer will be happening. If it is 0, then nothing will be transferred. Fine. So that means I cannot send x to y all the time, right? That's why I cannot directly put a wire simply like this. So I shall have some switch in between that will decide whether I shall send or not. That's why this tri-state buffer is there from x to y. And this is the input of my tri-state buffer. If it is 1, then only I will transfer. If it is 0, I won't transfer. So I hope this direction is clear for you now. x1 to y1. I have a wire, I have a tri-state buffer, and here I have the switch of the tri-state buffer. Fine. Now I said this is a bidirectional bus. So this is not the only way to communicate. I have to communicate back also. Means y1 to x1 also I shall have some way to communicate. For that what I have to do? Again I have to draw a wire like this. Now I cannot directly put a wire because I have to decide whether I can transfer or not. That's why I have one more tri-state buffer here. That will decide whether my y1 to x1 can be transferred or not. Fine. So this is a tri-state buffer to communicate from y1 to x1, and this is the x1 to y1. For this tri-state buffer also I shall have some input line that will decide whether it's fine to transfer or not. This is the input line. So I hope this part is clear for you, right? Now when shall I send x to y or when shall I send y to x? I cannot send both together, right? Otherwise there will be some collision. So what we'll do? We'll put some signal from here C. C is the signal which will decide whether my transfer is from X to Y or Y to X. So how? Suppose C is 1. I am sending 1 as a signal here. If C is 1, see this 1 will be coming here and this 1 will be coming here. This tri-state buffer is getting 1. If it is 1, I know I can enable the transferring from X to Y. So this X1 to Y1 will be happening. Now what about this Y to X at the same time? See, this 1 will be coming here also. Now I am putting one NOT gate here. This is a NOT gate. So this 1 is becoming 0 here. And this 0 will be going to this tri-state buffer. Means this tri-state buffer is off now. This is on. So whenever C is 1, X1 to Y1 will be working. Similarly, if it is 0, if I am sending 0 here, then what will be happening? This 0 will be coming here and this is off. And this 0 will be coming here, this will become 1. So this tri-state buffer will work now. Means Y to X will be communicating. So this C will decide. I hope this part you understood. So these two parts are same only. They have shown some other components where you can send from X2 to Y2 or Xn to Yn. Same thing. There is nothing different. If you understood this part, that's it. Fine. Some more syntax we'll see how to declare the variables. Suppose again in bus and out bus. What do you mean by in bus and out bus? In bus are the buses through which you put the inputs to the hardwares. It may be register or ALU, whatever. And out bus are the buses from where you take the output from the hardwares. Fine. So we have two different types also in buses, in bus and out bus. In bus is used for inputs and out bus is used for to generate the outputs. Now suppose you want to transfer some 4-bit of information to a particular hardware through in bus. So this is how we write in bus 4. Fine. For out bus 4 means your out bus can carry out 4-bit of information. So once you have declared this is how also you can write A equals to in bus. So that again and again no need to write in bus. You can simply write A. Similarly, out bus B7 to 4 means from your register B, what I will do, the higher order 4 bits of information I will be transferring to the out bus. Fine. So next, a very important topic we'll discuss. The last important topic of today's video is several types of bus structure within the CPU. So this is very, very important for your exam point of view. We have 3 different types of bus structures within the CPU. First one is single bus oriented ALU. Second is 2 bus oriented ALU. Third one is 3 bus oriented ALU. So we'll see one by one. It will be more clear for you. Single bus oriented ALU. So if you see this diagram, this is single bus oriented ALU. So what it says, in single bus oriented ALU, we'll have a single bus only throughout the ALU and all other registers to perform any specific operation. You have only one bus. You can, if you want to use it as in bus, out bus, whatever you do, you have only one way to communicate. Means one set of wire to communicate. Fine. For in bus also, out bus also, you have to use this wire only. You don't have any other option. That's why if you see, everywhere it's connected through a single bus. This square is nothing but the bus only, the whole bus. This is bus. From here you are connecting here, from here to this to this. So everywhere connection is there. Every components are connected to each other, but through a single set of wire or single bus only. This architecture is single bus oriented ALU. So if anyone asks you to draw the block diagram for single bus oriented ALU, so what you can do is, no need to draw or no need to mention all the components in CPU, some of the major components which are very necessary to perform any specific arithmetic or logical operations, you can mention, otherwise no need. What are those? One ALU you need in the CPU, so you have to mention about ALU. Some general purpose registers, R0 to R5, Rn, whatever you take, so you have to consider that. These are the buffer registers, so that if there are some traffic, then it will control it. Right, one by one I can transfer. So if there are multiple data you are transferring to the same register, then it will work as a buffer. I think you know already about the buffer register B. And this side we have a special purpose register. Now if you see, there are some new special type of registers we have, like frame pointer, base register, index register. So if you don't remember this this registers, then you can simply write all the previous old registers also, like PC, IR, MAR, MDR. That's also fine. These are some examples of special purpose registers. Fine. And you have a set of wire, only single set of wire to connect everything like this. I hope this is clear. Now if I ask you to perform a specific operation, say C equals to A plus B, I have to perform A plus B. This is the operation I am giving to you, or A equals to A plus B, whatever. A equals to A plus B or C equals to A plus B. Now if I ask you how much time it will take to perform C equals to A plus B whenever you are using single bus architecture, by assuming that for each instruction to be executed, I need one clock cycle. Now how much time it will take? See here, let me explain this. What is the operation? C equals to A plus B. For that I need A and B, then only I can go for A plus B. Now see here, I have only one set of wire. To get A in ALU, I need one clock cycle. I have only one way, right? So at the same time I can send only A here. So in one clock cycle I am getting A in ALU. In the next clock cycle I will get B. I cannot have A and B together because I have only one wire, right? Only one data can be sent at the same time. So in one clock cycle I am getting A, in second clock cycle I am getting B, right? Now to perform A equals to A plus B, this is a very simple math for computer, right? I cannot say that it will take one clock cycle. The time will be very less. It will be milli nanosecond. You cannot say that it will be one clock cycle for performing only this A plus B. So in one clock cycle we'll get A, second clock cycle I am getting B. In third clock cycle I will perform this operation and send this output to the output buses. So I need total 3 clock cycles to perform C equals to A plus B for this. Now many of you will say, sir, how 3? It should be 4, because to perform A plus B also I need some time. Yes, I need some time, but A plus B is very minimum. It's a very simple math for computer. Your computer can perform very high-fi maths. A plus B is nothing for him. And your computer can really perform this A plus B in very negligible time. So I cannot consider this as a single clock cycle. If you are giving some very complex maths, maybe integration, then so many complex maths, then it may take one clock cycle, but for A plus B, no. So that's why I'm ignoring the time requirement for performing A plus B. So total 3 clock cycles. Fine. One is for A, one is for B, and one is for to get the output. The time requirement in ALU I'm neglecting because this is very simple. Fine. Now let's see the 2 bus architecture. In 2 bus architecture, see, instead of one bus I have 2 set of wires or 2 buses here. So if I have 2 buses, I can simply modify the architecture like this, right? And general purpose register also I can have 2 ways to communicate. Then I have special purpose registers. This side, special purpose registers also I can have divide into 2 parts now, right? In previous case I had only one set of special purpose register. Here I can divide the same set of registers into 2 parts, or here also you can put 2-way communication, it's fine. So first part of a special purpose registers I am attaching with A, and second part with B, so that anyone can access from anywhere. Fine. In ALU also I have 2 ways to get the inputs, and then output also can come to any one of these way. I hope the architecture is clear. Now the question is, how much time it will take to perform C equals to A plus B using this architecture? Can you tell me? Yes, exactly 2 clock cycles. In the previous case it was 3 clock cycles, now I need 2 clock cycles. Why 2 clock cycles? See, I have 2 ways to get the data. So in one clock cycle I will get A and B both. In previous case I did not get A and B together, but here I have 2 ways. So in one clock cycle I am getting A and B, and the next clock cycle I will just send this output to the any one of this wire or any one of this bus. Fine. And the time requirement I am neglecting because A plus B is very simple. I hope you understood why it's 2 clock cycle, one to get the input and second one to get the output. That's it. Fine. Now the third one is 3 bus oriented ALU. So in 3 bus oriented ALU, see the architecture. Now I have 3 different buses, A, B, C. Fine. If you see this architecture, all the components are connected through 3 different buses now. Now, if I ask you the same question, how much time it will take to perform C equals to A plus B, can you tell me? Yes, you are correct. one clock cycle is enough to get the output now. Why? How? Because in one clock cycle only I will get A and B. There is no doubt, right? I have two connections from here. And I have an output connection also in some other wire. I don't have to depend on the same wires, right? Or I don't have to wait for this wire. I have a dedicated separate wire. So in one clock cycle only I am getting A and B. Since this time requirement is negligible to perform A plus B, I am considering only to get the output. So immediately I can get the output, right? If this is nothing, then I am getting the input, I am getting the output. Fine. So in one clock cycle I can perform the operations. So these were some basic topics from control unit. In the next video, we'll start the hardware approach to design a control unit. So I hope you liked the video. Thanks for watching my video.